So last we left off, we were talking about electronegativity. Am I making it up? Anybody remember what electronegativity is? Anyone? Anyone? Okay, so electronegativity kind of helps us dictate whether things are going to be polar or non-polar. We're talking primarily bonds between two atoms. So for instance, excuse me. For instance, if we have, say, carbon and oxygen. So if we had carbon and oxygen, the way that we would determine the electronegativity, we would basically look at the electronegativity table. So basically, Pauli basically had made arbitrary numbers for all of the elements based upon the energy it took to break them. And so he found that basically fluorine is really, really strong, right? So it has a really strong pull on electrons, where something like lithium is pretty weak. It has a really weak pull on electrons. So lithium is more likely to give up an electron. Fluorine is definitely going to be taking an electron. And so if they're sharing, right, you have two molecules or two nonmetals that are sharing, what's going to happen is that the one that's going to be strongest is going to pretty much want to take if it's within a certain range. Okay, and the way that we determine that is we basically look at the electronegativity number, let's say for carbon and oxygen. So oxygen is 3.5, which is greater than carbon's, which is 2.5. So we'll put oxygen's first, and then we subtract what carbon is. So in this case, we get a 1.0. So there's a scale that kind of lets us know if it's polar or if it's non-polar. So if it's 0 to 0, what would you say? If it's 0.4 less than or equal to 0.4 less than or equal to the 0.4, then it is considered to be non-polar. If it's 0.4, greater than 0.4, but less than 1.8, it's considered to be polar. And then if it's greater than or equal to 1.8, it's considered to be ionic. Okay, so one would be polar or non-polar or ionic.
Polar.
Okay, so in this case, this guy is going to be polar. Pretty simple. Yeah, no, maybe. Anybody alive?
Yes.
Yeah.
Yeah.
Yes.
Okay, good. Okay, so this is that table that just basically tells you exactly what I told you. So pure covalent basically means non-polar, another way of saying non-polar. Okay. So I'm gonna put you guys in groups, put you there for like, well, maybe not a group, since there's so many of you guys. God, it's just so crowded today. Okay, so you guys, I'll put you in groups, and then I want you guys to determine which ones are polar, which ones are non-polar, and which ones are ionic. And then also, let me share this with you while I'm talking. So in the case of CO, since oxygen is greater than carbon, this guy, and since we know it's polar, the electron is gonna be favoring the oxygen. So it's gonna have a partial negative charge associated with it, where carbon is gonna have a partial positive charge associated with it. So the polarity is going towards oxygen because we're basing it upon electron polarity, okay? Are you guys good? You understand?
Yeah.
You understand what I'm asking you to do?
Yes, I think so.
Okay. Okay, I'm gonna put you in a group, one big old group, and you guys can hash it out. Let's see. And you guys will have 6 minutes. Room's open. Okay, everybody's back.
Yep.
Okay, show me your skills.
Do you want me to select carbon, hydrogen? The difference is 0.35,
Okay.
which makes it non-polar.
Okay.
And
so you guys can write on my screen. You don't have to tell me. Write on the screen.
Okay, I will.
I'm being lazy. Only I am allowed to be lazy. That's right, Michaela. You're not used to me being online.
Yeah, not exactly.
This is a totally different class.
I'm just gonna say P for polar.
Okay.
And then this guy's the partial negative, and that's the partial positive.
Okay.
And then I'll do the next one, and I'll let all you guys do the one after that. Hold on. Don't get enough space. This is a little bit sloppy, just a little bit. And so for this one, oxygen is positive, partial positive, carbon's partial negative. All right, well, looks like it's all you, Leah.
What did you call your sister?
Leah, like short for Angelia.
Okay.
Yeah, just LIA.
Okay.
Dr. Henry, I read your message as type it in the chat for some reason.
I know. I put an extra E. You know, I'm being fancy, that's all.
This is a French class now.
I see.
That's right.
I know how to speak French, just add an E at the end of every word.
It's a hybrid chemistry and French.
Okay. Yes, Mauricio, you're good. And Leah looks good. So which one is partial? Yeah, there you go. Good job. Good job. Piece of cake, right? Simple.
Yes.
Okay. So this brings us to Lewis dot structures, right? So our Lewis symbols. Go clear, clear. You guys can see my full screen, or do you see only my little screen? You see the full screen. Okay, so for Lewis symbols, we basically use dots to represent the number of valence electrons that a atom has. Like for instance, calcium, if you guys remember, periodic table, calcium is argon 4s2, meaning that there's only 2 valence electrons. This is the electron configuration. And so we'd represent it as Ca with 2 dots. Okay. How many valence electrons does oxygen have?
Six.
So oxygen has 6 valence electrons. So we would represent it having 6 dots around it. How about fluoride? I mean fluorine. Oops, not 8. I'm just adding dots.
Seven.
7. Okay, simple.
Mm-hmm.
Good. Okay, so this just basically shows you the electron configuration and the number of valence electrons each of those atoms would have. Okay, so we know just from kind of working with things, we know that sodium wants to be like neon. And so it wants to lose an electron, right? We've kind of talked about that before. And so in this case, this basically showing you with the Lewis dot structure that sodium now is going to lose an electron. And so it has a free electron to kind of trade or to give away. So when we do the Lewis dot structure for this, we want to put brackets around here, even though we don't have brackets on there. And then that plus should be on the outside. So let me clean this up a little bit. I've got to fix my lecture notes. I was stealing this image from the book. Okay, so in the case of calcium, calcium wants to lose 2 electrons. So to be like argon. So again, we draw it as if it has that plus charge and then put it in brackets to let us know that the old thing is charged, but it doesn't have any of those electrons. And then in this case, chlorine wants to gain 1 electron. So if we add an electron to it, then we have the chloride ion. Sulfur wants to gain 2. Then we have the sulfide ion. Okay? Simple?
Mm-hmm.
Yes.
Okay, so if we put these 2 components together, we can also show an ionic compound forming by Lewis dot structure. So in this case, sodium is going to be losing an electron, and chlorine is going to be gaining that electron that it lost. So then we would just put this guy in brackets, and also the sodium should also be in brackets with the plus charge on the outside. And then in the case of magnesium, we're going to be losing 2 electrons, and oxygen is going to be gaining 2 electrons. So then we're just transferring the electrons. Simple. You see how it works?
Yeah.
Yeah.
Now, when we're talking about covalent bonding, electrons are being shared. So let's say we're making chlorine, the molecule, from 2 chlorine atoms. So in this case, each chlorine has 7 electrons around it. They're going to be sharing. Each one is going to be providing 1 electron to the other so that they're sharing, so that we can actually reach what we call our octet. We can be like a noble gas by having that outer shell full, by having 8 electrons around us. So if we look around chlorine here, it has 2, 4, 6, 8 electrons around it. And so this chlorine also has 8 electrons around it. So its octet has been reached, so it's going to be happy. Okay? The electrons here that are just around the chlorine, these guys are called lone pairs. Okay? This guy is going to be shared, so we'll often draw it like this, with a single line between it representing that bond, that single bond. Okay? So hydrogen, on the other hand, has 1 valence electron. The other hydrogen also has 1 valence electron. So hydrogen only wants to be like helium. Helium has 2 electrons surrounding it. So the most that hydrogen can have surrounding it is 2 electrons. So it's going to only make a single bond. So because it only can make 1 single bond, it's never going to be a center atom if there's multiple elements in a compound. So you'll never have something like this. This would never happen, right? Because hydrogen can never be a center atom. Does that make sense?
Yes.
Yeah.
Okay. I know this is a recap. You guys all know about this already, right? So instead, carbon will be the center atom. Because carbon can make 4 attachments, and it's able to reach its octet, 2, 4, 6, 8 around carbon. Each of these hydrogens have 2 electrons around it, so their octet is full as well. Okay? Questions, concerns, Cash?
No.
Okay. Let's see. Okay, so again, the octet rule is basically when you're getting that outer shell fill, and the outer shell basically means that the S and the P orbitals are completely full, and that's a total of 8 electrons surrounding that atom, okay? And so, again, everybody wants to be like a noble gas. Noble gas has its outer shell fill. It has 8 electrons around it, and that's what's going to make it happen. So that's our goal. Try to make sure that we complete the octet rule, meaning octet meaning 8 around it. Okay, so for example, here we have carbon tetrachloride, and we have solidane, right? So in this case, again, we have carbon that's going to be in the center. And the reason why carbon would be in the center, because carbon has a weaker electronegativity than chlorine. So the guy who has the weakest electronegativity is typically going to be put in the middle, or the guy who basically can have the most things that can attach to it often will be put in the middle. Okay, so carbon can have 4 bonds attached. So we're going to stick carbon in the middle. And that's the same thing with silicone here, right? So carbon has 4 electrons. So it's going to be able to contribute its 4 electrons. So that's going to be one of carbons. Carbons, one of carbons. This is going to be one of carbons. And then the 7 are going to belong to chlorine. Right? So when they come together, they're able to form their bonds. So if we count, and I believe in trying to keep an account of all of the valence electrons that you have. So if we have 4 times 7, how many electrons would that be?
28.
Plus the 4 that's given to carbon, given by carbon. 28 plus 4.
32.
So we have a total of 32 electrons to work with. Now this becomes more important when you're doing more than just single bond, right? In this case, all you have to do is just count to make sure that you have the right number of electrons total. So you have 2, 4, 6, 8 around this carbon. You have 8 around this. 8 around this chlorine, 8 around this chlorine, 8 around this chlorine, 8 around this chlorine, and we have 8 in the middle. And we're going to count all of the electrons surrounding the whole molecule: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So a total of 32. So everything is accounted for. Simple?
Yeah.
Okay. So Mauricio. Oops. U-R-I-C-O. Leah and Michaela. Mikey. Okay, so draw the Lewis dot structures for these guys. And Mauricio, dictate what you want me to draw. I know, you got to tell me. Mauricio, who's going to be in the middle? Okay, so N's going to be in the middle with 3 H's around it. Anything else? Any lone pairs? Two electrons on the top. A lone pair on the top. Piece of cake, rough day.
Yeah.
Okay, good. Okay, so this is basically showing you single bonds that are forming around these atoms, right? So sometimes we have to use double bonds to reach our octet. So like in the case of formaldehyde. So for it to be able to reach its octet, we have a single bond between carbon and the hydrogen. single bond here between carbon and hydrogen, and a double bond between oxygen, carbon, and oxygen. And a double bond is basically sharing 4 electrons, okay, with, in this case, 2 lone pairs. So oxygen reaches its octet, carbon reaches its octet, and both of the hydrogens reach their octet. Okay, same thing happens here with ethylene or ethane. So the carbons have to use a double bond to be able to reach its octet, and single bonds with each of the hydrogens. So there are 8 around this carbon, there's 8 around this carbon, and there's 2 around all of the hydrogens. So sometimes we have to use a triple bond. Okay, so in this case, we have carbon monoxide. Right? So triple bond is sharing 6 electrons. Okay, so the way that it's able to reach its octet, we have 8 around this carbon, 8 around this oxygen, and so triple bond works out well for this. Okay, and here's another example with the cyanide ion. So the only thing that's different here is that nitrogen has how many valence electrons?
5.
5. And carbon has how many valence electrons?
4.
4 plus 5 is what?
An odd number.
Is 9, right? So we notice that it has a negative charge. That lets us know that there's an additional electron added onto it. So altogether, that's going to be 10 electrons. 2, 4, 6, 8, 10. So we have enough electrons. Piece of cake?
Yeah.
Okay, so let's test it out. Okay, so Mauricio, can you do this guy for me? Mikey? And is it, you say Leia? Okay, tell me what I need to do, Mauricio. Okay, and in the middle, oh, I forgot one thing about this guy. It should have brackets around it, and then it should have that minus on the outside. So you want to put brackets around here and the plus, because we're short 1 electron, right? Is that true, Mauricio?
Yeah, that's true.
Okay, piece of cake.
Mm-hmm.
Good. Okay, so we can also use the Lewis dot structures to help us do chemical equations to kind of see what's going on. And this is basically just showing you that. Not too hard. Yeah, no, maybe?
No.
Okay, so the rule is, did I stop here? Yes, I did stop here. Okay, so these are just basically the rule, the kind of a step-by-step on how to do it. But you guys are feeling pretty good. You feeling confident on how to do these things?
Yeah.
Okay, good. Okay, so what time is it? Six 6:30.
6.
I mean 6:13. Sorry. It's been a long day. It has really been a long day. Okay, so I think I actually stopped at this slide for the other class. Not 100% sure. So I don't want to get too far ahead of the other class. So I think I'm going to stop here. So do you guys want to talk about the lab?
Yeah.
Yeah.
Oh,
Or
I
do you
was
guys-
We're gonna
to, I made that like spec. Oh, I can never say the word correctly, but the
Spectrometer?
thing, spectrometer. I made like the mini one, I think on accident. I was confused because it looked like there were two different ones for me to make.
So did you have your sheet and your black piece of paper?
Yeah, and I made one, but it looked like there was a larger one you could also make. I don't know.
Okay. You used the template, right? It's pretty small. Where's mine? I made it last night.
I did use a template, but like so when you go to the website, there's like a link to a PDF and that has a template on it as well. And then there's like a different template and they're both on the same website. I was like, I don't know which one to use, but I made one.
Yeah,
I think it'll work.
The one that I gave you, both of them will work. They should work the same way. One is just it's easier to build in theory than the other.
Oh, I see. Okay, yeah. I just want to make sure that was fine because I noticed there were like two different templates.
Yeah.
Hey, Mauricio. So I was gonna think of setting up a Zoom meeting around 2 p.m. tomorrow, and probably another one Friday morning.
2 p.m. tomorrow, and then Friday morning at what time?
Like 9.
Yeah, that's good for me.
All right, for sure. I was gonna send out an email to everybody else.
Yeah, we need to get that done.
Yeah.
Not that we don't have it done, but you know.
Yeah, no, we've definitely already met plenty of times and they're basically, I mean, we already finished the presentation really.
Just the small details, you know.
Yeah. We actually, don't worry, Dr. Henry, we just need to work on the cover sheet. That's all we have left.
Okay. Okay. So do you guys want to go ahead? What if you guys want to go and grab all your goodies and then we can meet in a lab, we'll say in, you want to say 10 minutes? That be enough time for
Okay.
you guys?
And you want, that's the second link, right? The one that's
Yeah.
underneath. Okay.
That we haven't used yet. I can.
Yeah, I will see you in 10 minutes then.
Okay. I'll see you guys in 10 minutes.
Sounds good.
I may have a beer in hand at that point, but see you guys in 10 minutes.
Okay.
Okay.
Mhm.